I thank organizers for giving me an opportunity to talk here. Today, I discuss a non-trivial connection between the theory of open quantum systems and thermalization of isolated systems. Okay, so this is an outline of my talk. So first, I start with a general introduction. And then I present the main result on the float systems. In my talk, I consider the Ljubljana gap of the bulk dissipated quantum many-body system. And here I discuss the general behavior of the Ljubljana gap in the weak dissipation regime. And I argue that it is somehow related to the thermalization dynamics of the isolated system. But it turns out that there is an essential difference between the float and the static systems. So I discuss the static system separately here. And in static systems, I argue that not the standard Ljubljana gap, but its variant named as a projected Ljubljana gap contains relevant information on thermalization dynamics. Okay, so let's start the introduction. So needless to say, it is a long-standing fundamental problem to figure out how and why an isolated quantum system thermalizes. Experimentally, the quantum thermalization has been observed in cold atom experiments, and theoretically, it is recognized that the so-called eigenstate thermalization hypothesis explains thermalization. So according to the ETH, the local operator has a random matrix structure, which is summarized over here. So this first term implies that the diagonal matrix element is a smooth function of the energy density. So this property ensures that the long-time average coincides with the ensemble average. Second, here, this S is the entropy of the system, so this is an extensive variable. So this exponential factor implies that every off-diagonal matrix element is exponentially small. And this property ensures that the long-time fluctuations are negligible. And finally, this F is a smooth function of the energy difference and energy density. And the information on the finite time non-equilibrium dynamics is encoded in this function. So for example, if we want to evaluate the relaxation time under the unitary time evolution, we have to examine the function F in detail. But the ETH itself does not determine the function F. So it means that although the ETH explains thermalization in the long time limit, it does not tell us much about the time scale of the onset of thermalization. So in general, it is a difficult problem to evaluate the relaxation time under the unitary time evolution. For example, if we plot the eigenvalues of the time evolution operator, all of them lie on the unit circle in the complex plane. So this is due to the unitarity of the time evolution. So we cannot estimate the relaxation time just by looking at the eigenvalues. So in other words, individual energy eigenstates does not decay forever. And the thermalization proceeds by the complicated dephasing process among energy eigenstates. So in this way, it is an important but non-trivial problem to evaluate the time scale of thermalization. Okay, so cold atomic, ultra-cold atoms also provide an excellent platform to study the dissipative quantum many-body systems illustrated here. So this is a quantum many-body system which may be subject to external periodic driving. And the system is also interacting with the environment, which causes a dissipation. So in the Markovian regime, this kind of system is generally described by the Lindblad equation written over here. So this first term represents the unitary time evolution under the system Hamiltonian. And this second term represents the effect of dissipation. So this positive parameter gamma controls the strength of dissipation. And the operator Li here is called a jump operator, which characterizes the dissipative process at site I. Here, I assume that the dissipation is acting to the bulk of the system. So this summation is taken over all the lattice sites. The recent cold atom experiments enable us to introduce the well-controlled dissipation to a quantum many-body system. So it means that we can experimentally implement a simple jump operator Li, and we can also tune the parameter gamma freely. So such an experimental progress opens a new field that is called the dissipation engineering. So its purpose is to create novel phases of matter by utilizing dissipation. Yes. Sorry? Okay. So the derivation of the Lindblad equation is has several subtle problems, and usually this equation is justified for a small gamma. But in some case, we can derive the Lindblad equation for strong gamma regime. But yeah, it is. In the Markovian yet strong dissipation is possible in some case, but it is beyond this talk. Okay, and usually in this context, the Nobel physics emerges in the strong dissipation regime. So the open quantum many-body systems in the strong dissipation regime are now intensively studied both theoretically and experimentally. But in contrast, the generic properties in the weak dissipation regime are not paid much attention. But it does not necessarily mean that the weak dissipation is not interesting or not important. So I want to say that the strong dissipation and the weak dissipation have different roles. The strong dissipation can be used to create a novel quantum material. So this is suitable for the purpose of the dissipation engineering. On the other hand, the weak dissipation can be used as a probe of the intrinsic properties of a given quantum system. So as pointed out in the previous talk, the weak dissipation can be regarded as a probe field to the system. So more specifically, I expect that the weak dissipation can lead to better understanding of thermalization dynamics of the isolated quantum system. So this is my motivation to consider the open quantum many-body systems in the weak dissipation regime. So that's the introduction. So in the following, I discuss the general property of the many-body Lindblad equation in the weak dissipation regime. Okay, so now I explain the theoretical setting. So I consider the Lindblad equation describing a quantum many-body system under bulk dissipation. So this is a general Lindblad equation. The generator of the dynamics is denoted by L of t. So this is called Ljubljana or Lindbladian. Here, we may apply the periodic driving field to the system. So the Ljubljana is time dependent, and this tau is a period of the driving field. So the following argument is very generic, but here to be specific, I consider the kicked edging chain under bulk dephasing as a theoretical model. So this is a Hamiltonian. So this is a spin 1/2 quantum edging model, which is driven by the periodic pulse of the transverse field. The bulk dephasing corresponds to the jump operator sigma z at every site I. So our Ljubljana is simply written like this. So this is our theoretical model. And the parameters of the Hamiltonian fixed in this way. So in this case, the system is in the quantum chaotic regime. Okay, so next I explain the physical quantity of our interest. So that is the Ljubljana gap G. So in order to define the Ljubljana gap, I consider the time evolution operator over one cycle of the periodic field. So this is referred to as the Floquet operator. Then the eigenvalues of the Floquet operator are denoted by exponential of lambda alpha tau, and these lambda alpha are simply called Ljubljana eigenvalues. So it is shown that the Ljubljana eigenvalues have non-positive real parts, so they are ordered in this way. So here lambda 0 is 0, so this corresponds to the steady state. And for simplicity, I assume that the steady state is unique, and all the other eigenvalues have negative real parts. Then the Ljubljana gap G is defined as the minimum decay rate among the eigenstates. So it is simply given by the minus of the real part of lambda 1. So, and this is a numerical demonstration of the Ljubljana eigenvalues for relatively small system size. So here, this is a 0 eigenvalue corresponding to the steady state. And this one is the first excited state that gives the Ljubljana gap. Okay, so the reason why I focus on the Ljubljana gap is that it has several important properties. So first, the Ljubljana gap gives the asymptotic decay rate in the long time limit. So this is the formal solution of the Lindblad equation is expanded in terms of the right eigenvectors of the Ljubljana in this way. Then in the long time limit, the first excited state becomes dominant. So we have an exponential decay with rate g. So in this way, the Ljubljana gap determines the decay rate in the long time limit. And second, a finite Ljubljana gap in the thermodynamic limit implies the exponential decay of the spatial correlations in the steady state. This is also important because it means that the Ljubljana gap contains important information on the steady state. And the dissipative phase transition is always associated with the closing of the Ljubljana gap. So it means that the striking phenomena like the phase transitions can be investigated by calculating the Ljubljana gap. So in this way, the Ljubljana gap is a fundamental quantity in the theory of open quantum systems. So in the following, I consider this quantity. Okay, so now I'm ready to present the main result. So I consider the Ljubljana gap in the weak dissipation regime, and I find the Ljubljana gap generally behaves in this way. So when gamma is roughly smaller than V over L, where V is a Lip Robinson velocity, which characterizes the local energy scale of the system Hamiltonian, then the Ljubljana gap is roughly proportional to the product of gamma and L. So it means that if we increase the system size, the Ljubljana gap also increases. But if gamma exceeds V over L, then the Ljubljana gap becomes almost independent of the system size. So there are two regimes, and there's a crossover between these two. But you may find that if we take the thermodynamic limit, this first regime disappears. So the thermodynamic limit of the Ljubljana gap remains finite, even in the limit of gamma going to 0. So yeah, in general, this G bar is a positive constant. So if we take the weak dissipation limit after the thermodynamic limit, the Ljubljana gap tends to G bar. So this is positive. So it is a bit surprised because if we take the weak dissipation limit before taking the thermodynamic limit, the Ljubljana gap trivially goes to 0. So, okay, so it is trivial because if we take the gamma 0 limit, the dynamics becomes unitary. So the Ljubljana gap is 0. So this finite Ljubljana gap in the weak dissipation limit is a genuine many-body phenomenon. Okay, so this is a numerical demonstration of this main result. So I calculate the Ljubljana gap and plot it as a function of gamma for different system size. And as you see, when gamma is very small, actually the Ljubljana gap is proportional to gamma and the system size. But if gamma increases, then the Ljubljana gap becomes almost independent of the system size. So this is consistent with this general behavior. Okay, and this positive constant G bar can be extracted from the numerical data for finite size system by extrapolating the data belonging to this second regime towards gamma equals 0. So this is our estimate of the constant G bar. Technically, the extrapolation is done by fitting the quadratic function to the numerical data. So in this way, we can get the constant G bar. So clearly, it is positive. Yes. Okay, I explain later. Sorry, G bar is yes, G bar is a constant function of the tau. Yes. Okay. So now I explain a key idea behind this result. So that is the relation between the operator spreading dynamics and the Ljubljana gap. So yes, yeah. If we look at the transient dynamics, then you may find such a diffusive relaxation, but the Ljubljana gap governs the long time decay rate, so appearing in the asymptotic regime. So yeah. Oh, yeah, it's an important problem, and I think it depends on the model. And in this case, I think that the crossover time to the asymptotic regime does not diverge in the thermodynamic limit. But I don't remember correctly. Okay. Yeah, yeah. Density of states near 0 eigenvalue. Okay, I'm not sure, but in a bulk dissipated quantum medieval systems, often the eigenvalue, the Ljubljana gap is isolated. So we have a finite Ljubljana gap, so from the zero eigenvalue, and yeah, there are many the discrete eigenvalues, and in this sense, the density of the state is zero, or yeah. But it also depends on the model. Okay, so now I explain this slide. So first of all, I ignore the effect of dissipation, and I consider the time evolution of an operator in the Heisenberg picture. So, and I consider the time evolution of this local operator acting to this site. So even if the operator is strictly local at the initial time, it spreads over the system and it becomes non-local after the unitary time evolution. And this process is known as the operator spreading, and this is intentionally studied recently in the context of the quantum entanglement scrambling. So now I consider the effect of the weak bulk dissipation to this operator dynamics. Because the dissipation is acting to each site independently, it is expected that at the initial time, this operator will undergo the exponential decay due to the dissipation happening to this path. So yeah, so this operator shows the exponential decay during a short time interval delta t. So this is a very rough argument. But in a later time here, the operator spreads over the system due to the unitary time evolution in the sense that the operator becomes the product of the single site operators. Then, important point is that each single site operator will undergo the exponential decay like this. So this product of the three single site operators has the decay rate 3 gamma. So in this sense, the decay rate increases with time. In the same way, at a later time, the decay rate becomes 5 gamma and so on. So as a consequence of the operator spreading, the decay rate increases. And generally speaking, the instantaneous decay rate under the bulk dissipation is roughly proportional to the product of gamma and operator size. So it means that in a many body system, even if gamma is very, very small, such a weak dissipation can be amplified by the operator spreading dynamics. This is a very simple but important observation. Okay, so based on this consideration, we can guess the general behavior of the Ljubljana gap in the weak dissipation region. So when gamma is very small, we expect that the effect of dissipation can be ignored up to a time scale proportional to 1 over gamma. And if we can ignore the dissipation, the operator size increases linearly in time in the one-dimensional short-range interactive systems. But after this time scale T gamma, we expect that the operator size is saturated due to the balance between the operator growth due to the unitary time evolution and operator decay due to the dissipation. So from this consideration, we can guess that the operator size in the long time limit is given like this. So when gamma is smaller than V over L, then the operator will spread over the entire system before the dissipation takes place. So the operator size becomes a proportion to the system size. But if gamma is larger than V over L, then the dissipation takes place before the operator spreads over the entire system. That's why the operator size will be saturated at a finite value. So this is proportion to 1 over gamma. Okay, yes.
And so, you know, in the system periodic, basically what's important is diffusion, which is much slower. This is like ballistic.
Yeah. So this is ballistic. So it is known that the operator spreading occurs ballistically in the even in the chaotic system. Yeah. Yeah, it does not show up. Yes. Okay. So by using this result, we can obtain the general behavior of the Ljubljana gap. Yes. Yeah, honestly, I don't fully understand it. So, for example, if we look at the, for example, transport of the conserved quantity like the energy, then in chaotic case, the transport is often diffusive. But even in such a case, the dynamics of the operator is ballistic. So, yes. Yeah. Yeah. Thank you for your question. Okay, so here, as I explained, the Ljubljana gap is nothing but the asymptotic decay rate. So it is obtained by the product of gamma and the operator size in the long time limit. So by using this result, we can get a main result. So, and from this result, we can conclude that if we take the weak dissipation limit after the thermodynamic limit, the Ljubljana gap tends to a certain constant, positive constant G bar. Okay, a remaining problem is to understand the physical meaning of G bar. Okay, so in the following, I argue that, so it is natural to conjecture that this G bar corresponds to a quantum analog of the leading Luer-Polycott resonance in the classical chaos theory. So I explain the Luer-Polycott resonance later, but it describes an exponential decay hidden in the unitary time evolution. So it means that, so this G bar gives the time scale of thermalization. So before explaining the Luer-Polycott resonance, first I show you numerical evidence of this, the validity of this conjecture. So I consider this is the time evolution of the expectation value of the energy for the Kick-Daging chain. And the solid lines are obtained by numerically solving the Schrödinger equation without dissipation. And dashed lines show the exponential decays predicted by the Ljubljana gap analysis. So that is the exponential of minus G bar T. As you see, the numerical solution of the Schrödinger equation actually exhibits the exponential decay, and the decay rate excellently agrees with G bar. So in this way, we can estimate the time scale of thermalization by solving the eigenvalue problem of the Lind-Bradian. So it shows a non-trivial connection between the thermalization of an isolated system and the coherence of an open quantum system. Okay, so now I explain the Luer-Polycott resonance in the classical chaos very briefly. So let us consider the trajectory in the classical phase space. Yes. Yep. Yeah, there is no classical limit. Yeah. Yes. So I explain. Yeah. Okay, so now I consider the trajectory in the phase space, but instead of tracking a single trajectory, let us consider the ensemble of trajectories, which is expressed by the probability distribution P of gamma. And so its time evolution is simply given like this. So then we can formally define the time evolution operator for the probability distribution. So this is referred to as the Frobenius-Perron operator in the literature. And importantly, this Frobenius-Perron operator is known to be unitary in the Hamiltonian dynamics. The spectrum of the Frobenius-Perron operator is defined by the singularity of the resolvent operator defined like this. So for example, the eigenvalues correspond to the poles of the resolvent, and the continuous spectrum corresponds to the branch cut. But anyway, the time evolution is unitary. So the spectrum of the Frobenius-Perron operator lies on the unit circle in complex plane. So this is very similar to the quantum case. But the important difference is that if the dynamics is chaotic, then the Frobenius-Perron operator has a continuous spectrum on the unit circle. So this is an important point. So, and as I explained, the continuous spectrum corresponds to the branch cut of the resolvent. So it means that we can perform an analytic continuation of the resolvent from outside to inside the unit circle through the continuous spectrum. Okay. Then we can go to the second Riemann sheet, and you find there are several poles inside the unit circle in the second Riemann sheet. And these poles are written as exponential of nu it, and these nu I are nothing but the Luer-Polycott resonances. So this is the definition. And this nu I can be interpreted as a generalized eigenvalues of the Frobenius-Perron operator. And the leading real-Polkot resonance is defined as nu I with the maximum value of the real part. So that is the closest to the unit circle. Okay, so by using the real-Polkot resonances, it is shown that we can express the time evolution of the expectation value over a certain physical quantity A as a sum of exponential decays in this way. So this summation is taken over all the real-Polkot resonances. So if we take the long time limit, then the leading real-Polkot resonance becomes dominant. So we have an exponential decay. So here I emphasize that the real-Polkot resonances are determined by the Frobenius-Perron operator, so they are independent of the physical quantities. So it means that any physical quantity exhibits an universal exponential decay that is governed by the leading real-Polkot resonance. So in this way, the real-Polkot resonances can describe the exponential decays hidden in the unitary time evolution. So we can estimate the time scale of thermalization. Okay, but the problem is that, yeah, as I explained, the real-Polkot resonances are defined by the analytic continuation of the resolvent, but it is practically impossible to calculate the analytic continuation of the resolvent. So, but in the theory of classical chaos, it is known that the real-Polkot resonances can also be characterized by introducing the weak stochastic noise to the deterministic Hamiltonian dynamics, instead of directly performing the analytic continuation of the resolvent. So we have, so far we have considered Hamilton's equation of motion, but now I add the random Gaussian noise. So we have a Langevin equation like this. So epsilon is the noise strength. Then the corresponding time evolution operator, time evolution of the probability distribution is given by the Kramers equation written over here. So because of this diffusion term, the time evolution is no longer unitary. So the time evolution operator has eigenvalues inside the unit circle. So it is trivial. But an interesting point is that if the classical dynamics without noise is chaotic, then it is known that some eigenvalues of this time evolution operator with noise are still inside the unit circle, even if we take the weak noise limit. So it means that the zero noise and zero noise limit are different. And these non-trivial eigenvalues are nothing but the real-Polkot resonances. Okay, so then maybe you find a clear analogy between the classical case and the quantum case. In the classical chaos, the real-Polkot resonances can appear as eigenvalues of the Kramers operator in the weak noise limit. And our conjecture on the quantum case is that the real-Polkot resonances appear as eigenvalue of the Lindbladian in the weak dissipation limit. So in this sense, our conjecture can be regarded as a natural extension of the well-established result in the classical chaos. But here I want to emphasize an important difference between the classical and the quantum case. So in quantum systems, the bulk dissipation and the thermodynamic limit are crucial to get the real-Polkot resonance. So as I explained, the continuous spectrum is important to get the real-Polkot resonance. So because of the presence of the continuous spectrum, we can do the analytic continuation from the outside to inside the unit circle. So in the classical mechanics, the continuous spectrum is ensured if the dynamics is chaotic. But in the quantum mechanics, any finite quantum system must have a discrete energy levels. So there is no continuous spectrum. Okay? So the quantum spin 1/2 system can have the continuous spectrum only in the thermodynamic limit. So that's why the thermodynamic limit is very important in the quantum case. Okay, so now I summarize the result up to here. So the thermodynamic limit of the Ljubljana gap is discontinuous at gamma equals 0. So we have some constant value in the weak dissipation limit. And this result is explained by the operator spreading dynamics. So the decay rate under the bulk dissipation is given by the product of gamma and operator size. So even if gamma is very small, the operator spreading can amplify the dissipation. So that's why we have a constant finite decay rate even in the weak dissipation limit. And this G bar corresponds to the leading quantum Ramanujan resonance. So it determines the exponential decay rate of the isolated system. And these results are numerically verified in the Kick-Leijing chain under bulk diffraction. Okay, so in the remaining part of time of my talk, I want to briefly discuss the difference between the static and the flock systems. Yes. Yes, so here, yeah. Okay, so yeah, that's a very important point. And I checked that, okay, of course, the Ljubljana gap at a finite gamma depends on the choice of the dissipator, but this extrapolated value does not depend on the dissipator. So if we consider another dissipation, we have the same constant G bar. So in this sense, G bar is intrinsic, express an intrinsic property of the system. So it is not a property of the dissipation. So I can show you a numerical result, for example, here. Okay, so here I consider a different dissipator. So this is okay, so the jump operator is here is sigma plus, and this is a sigma minus. And then, okay, so you get a Ljubljana gap here. Maybe, so orange one is the result for the dephasing dissipation. And this blue one is this dissipator. Yeah, very different, but yeah. So it is rather it is a very strong evidence that this G bar is corresponds to the dual polycot resonance over isolated system. But I cannot prove that this is should be independent of the dissipator. So this is an open problem. Okay. Okay, so now I explain, go on to the static systems. So in static systems, I find that the Ljubljana gap simply vanishes in the weak dissipation limit. So G bar is 0 in this case. So this result is consistent with the previous work by Shibata and Katra. So they analytically calculated the Ljubljana gap in the thermodynamic limit. And they found that so the Ljubljana gap behaves regularly at small gamma in this way. So if we take the gamma 0 limit, then the Ljubljana gap trivially tends to 0. So here I want to explain why there is a difference between static and flock systems. In flock systems, the key idea behind the result is that the large decay rate emerges as a consequence of the operator spreading. But in static system, the Hamiltonian is always conserved under the unitary time evolution without dissipation. So if we consider the time evolution of the Hamiltonian, then there is no operator spreading. So this picture is broken down. And actually, in static case, the Ljubljana gap describes the relaxation of the energy due to dissipation. But it is not related with the intrinsic relaxation of the system, where energy is conserved. So that's why in static system, we cannot extract the information of the intrinsic decay of the static system from the Ljubljana gap. But now I propose a method to extract the real polycot resonance in static systems. Yes. Yeah, if there is some local conservation law, then the same argument holds. Yes. So the chaoticity is very crucial. So I have assumed that the flock system is chaotic in the sense that there is no local conserved quantity. Yep. Okay, so in static systems, the Ljubljana gap does not correspond to the intrinsic decay rate of the system because of the local conservation law in the isolated system. But conservation laws in the isolated systems are fully encoded in the diagonal matrix element in the energy basis. So my idea is that if we discard all the diagonal matrix elements, we might be able to extract the intrinsic decay rate of the system. So for this purpose, I introduce a projection superoperator P, which acts to the density matrix in this way. So this project out the diagonal matrix elements. And then I define the projected Ljubljana as PLP, and its spectral gap is called the projected Ljubljana gap. Okay, my conjecture is that not the Ljubljana gap, but this projected Ljubljana gap gives the time scale of thermalization in the static systems. Okay, and now I compare the eigenvalues of the Ljubljana, which are plotted by the blue points, and with the eigenvalue of the projected Ljubljana, which are plotted by the orange circles. And interestingly, I find that the spectrum of LP is included by the spectrum of L. Okay. So it implies that our projection picks up selective eigenstates which are related to the intrinsic relaxation. So here is a Ljubljana gap, but the projected Ljubljana gap is much larger and given here. So my conjecture is that not this G, but this GP gives the time scale of thermalization. Okay, so now I plot the projected Ljubljana gap as a function of gamma. So it is different from the Flock case. Yes. Sorry, sorry. Maybe I didn't. Larger one, yes. Yeah, there's such a possibility. Yeah, yeah. Yes. Yeah. In some case. Yeah. If we increase the system size, okay. I don't know the generic feature of the Ljubljana values, but yeah. But yeah, I confirm that if we increase the system size for this model, then simply this eigenvalues go to approach to 0, and this is always the spectral gap. But yeah, it depends on the model. Yes. Sorry. Okay. Yeah. Okay. So yeah, this is my result. And okay, so it is different from the Flock system in the sense that this extrapolated value to gamma equals 0 depends on the system size. So we have a size-dependent value of GP bar by extrapolation. But if we plot the L times GP as a function of gamma, then we find that this extrapolated curve cross at gamma equals 0. So this implies that the GP bar is proportional to 1 over L. So, and I interpret it as a size-dependent real-Polypot resonance. And okay, so finally, I compare this exponential decay predicted by the projected Ljubljana with the numerical solution of the Schrödinger equation for larger system size, L equals 28. Then we find that this projected Ljubljana gap excellently reproduces the exponential decay rate of the isolated system. Okay, so this is a conclusion. And my take-home message is that the open system analysis may deepen our understanding of the isolated systems. Okay, thank you very much. Yeah, actually, yes, so it is not so trivial, but in a finite size system, usually the Ljubljana gap is finite. So in this sense, if we wait a very, very long time, then we eventually get an exponential decay. But okay, for example, in this case, the Ljubljana gap, yeah. Yeah, but for example, in this case, the Ljubljana gap is proportional to 1 over L. So if we take the sum-time limit, the gap vanishes. So in such a case, I think that if we take the sum-time limit, we get some parallel decay, but I'm not sure. Yeah. Yeah. Actually, it is a very interesting and important problem to extend this kind of result to the aperiodic driving. But I'm not sure how we can define the spectral gap, because in Flocky case, we can clearly define the generator of the dynamics by the time evolution operator over one cycle. But in the aperiodic case, I'm not sure how to define spectral gap or something.
So in the classical case, I mean, since you just put noise and no dissipation, so it should just heat up to infinite temperature, right?
Yeah.
But then there's no steady state. So, I mean, okay, like it'll just blow up the whole system.
So for example, if we consider unbounded classical systems, maybe we often introduce a friction term to realize the finite temperature state. And if we consider such a friction term, then we can follow the same argument, and then we find some non-trivial eigenvalues even in the weak noise limit, and it gives a decay rate at a finite temperature.
So the limit of noise going, the dissipation going to zero gives you some.
Yeah, some finite non-trivial eigenvalues. Yeah, thank you very much.